that said, you know, this one only magnifies 3 times. And the student said, oh my, I've already used it twice. All right, this should look familiar. We're not going to solve it. We're just going to set it up. A baseball diamond is a square 90 feet on the side. A runner starts from home plate towards first at 20 feet per second. How fast is the runner's distance from second base changing when the runner is halfway to first base? Just, how would you set that up so that it'd be ready to solve?
You know I'll be there. Just call me there. I was just thinking how like
okay. Here is the infield. The runner is running to first base. His distance, or her distance, is changing to second base. And so what we're trying to figure out is dSdt. That's what you're trying to figure. So you need to come up with an equation that has S in it. What information do you know? You know that the bases are 90 feet on the side. You know that this person is what?
45.
Halfway, so it's at 45. And we need to figure out S, which is pretty easy. You can use Pythagorean theorem. So we need to come up with an equation that has S in it. But remember, anything that's moving has to have a variable. So this 45, is that moving? Yes, so that's X. Is the 90 moving? No. So that can stay as a 90. All right, now what would the equation be that contains S? A squared plus B squared equals C squared. So X squared plus 90 squared equals S squared. That's the equation. You want to find dSdt. See, you don't have to make this a square root, because all we're looking for is dSdt, so just use implicit. So, derivative of this is 2x dx. What's the derivative of 90 squared? 0. And I bet you between A, B, and B, C, and you guys were just as guilty, people came up with a derivative for this. They went 2 times 90 and something like that. Okay, be careful. When it's a constant, the derivative is 0. And then it's 2 times s ds dt. We know x is 45. We know dx dt is either negative 20 or 20, whichever way you define it. You can solve for s with Pythagorean's theorem, and then ds dt. Okay. But this is dx dt. My mistake. Okay. No, this is dx dt, this is ds. All right? Okay. Okay, this is number 15, and I've already gone through it individually with a couple people, so rather than going through it individually 30 times, I think I want to go through it once. All right, you're given a function x, it's a curve, and you want to find the length of the curve from y equals 1 to 2. So you're going vertically, so you use the same formula except you do it with respect to y. So what is the length of the curve? It's the integral that goes from 1 to 2 to square root of 1 plus the x dy squared dy. That's the formula. Okay? So then, what is dx dy? I simply took the derivative of this with respect to y. So 3y squared over 6. I think of this as 1/2 y to the negative 1. So then the derivative would be a negative 1 y to the negative 2 over 2, which is negative 1 over 2 y squared. Okay? Any questions with that part? So then that gives me the integral from 1 to 2 square root 1 plus this thing here squared. All right. Then it gives you a hint. It says that this thing that we just wrote is a perfect square. Well, that would be nice, because if 1 plus a mess squared is a perfect square, it means it gives us a new mess that is squared. Well, if we take the square root of the new mess that is squared, what does it give us? Just the new mess without any square root. So that's why it's going to be nice, because instead of having 1 plus something squared, if that 1 plus something squared expanded out, becomes a perfect square, we can take the square root of it and it simplifies it. All right, we okay in the concept? So that's what we're trying to do, is make this thing here become a perfect square. All right. So now it's just algebra. This becomes 1 plus this thing squared out. So we're basically going... Well, it's not bad. You're going to FOIL it out. So we get y squared times y squared over 2, so it's y to the 4th over 4. Then you get this times that, which gives you y minus y squared over 4y squared, which is 1/4. And then we get the same thing there, minus y squared over 4y squared. And then plus 1 over 4y to the 4th. Okay? So now, it becomes the integral from 1 to 2 square root. This becomes 1 plus y to the 4th over 4. And then this is simply a minus 1/4 minus 1/4. So minus 1/4 minus 1/4 plus 1 over 4 y to the 4th. Okay? Which, one more step of simplifying, and then we'll talk about it. 1 plus y to the 4th over 4 minus a half plus 1 over 4 y to the 4th. All right, what we just did is we expanded this right here, and what we got was this. That's all we've done so far. But now, what can you do with this? You can take the 1, bring it inside, and add it to the negative 1/2, which makes the part inside a positive 1/2. So now we have y to the 4th over 4 plus 1/2 plus 1 over 4 y to the 4th. Okay? Doesn't this thing here look almost like that? The only difference is this is a minus, this is a plus. What was this? That was the extension of taking this perfect square and expanding it out. So now, let's just take this thing, put it back into a perfect square. What would it become? It would become, if this thing here was put back, it's put back looking like that. So this thing's going to be put back looking exactly the same thing, except it's going to be a plus because of that. So it's going to be whatever that was, y squared over 2, now plus 1 over 2y squared squared. If we squared this, that's what we would get.
Does it always work that way?
Does what?
So nicely, like if you...
Well, that's because there was the proper number was put here. If that wasn't a 1, then that wouldn't have been. But there are, through the years I've noticed there's been a lot of problems where you have to integrate. And you look at it and say, that's impossible to integrate. And usually what happens if you do the algebra and go through it, it goes and then it becomes a perfect square. So,
But how can you, is that something we should be able to recognize? Like the difference between those two, therefore,
no, the fact was that they gave you the hint.
Oh.
They told you that, hey, if you expand this out, you're going to get a perfect square. So, and I don't know if it's going to be on the AP test, but it's still something that you should at least be familiar with, that when you have something messy, and it's a square root, it's very possible that it'll become a perfect square and simplified if they're expecting you to do it by hand.
So, you expand out what's inside those parentheses in
Where are you at?
the blue circle.
Yeah, if you multiply this out, you get this, which gives you this, which gives you that. Well, that looks exactly like this once we add the 1 to it. The only difference is the plus sign. So putting this back in factored form, it will give us the same answer as the purple, but now a plus.
And what does that give us?
Well, now it gives us a square root of something squared, so what happens? The square root disappears, and you end up with just y squared over 2 plus 1 over 2y squared, which is a relatively easy function to find the antiderivative.
It is?
And it's not the same thing as what's in the red circle there?
This here is the same as the red circle.
Yeah, so that underneath to your right, the final answer, that's the same as what's in the red circle, right?
What's in the red circle is something squared, and when you take the square root of something squared, you just get the something. So this something is the equivalent of this whole thing. with the square root part of it. Okay? You know, an example would be this. And we'll be getting to that in chapter 8. Square root of 1 minus cosine squared. Not so sure what that is, but what's another name for 1 minus cosine squared? Sine squared. So you could rewrite this as sine squared, and the square root of sine squared is just sine. So now you're just integrating sine. So there's another case where you can simplify it down. Okay, let's get on today's task
Wait,
then.
how the y to the fourth over 4 plus half, I mean, the simplified y squared over half plus, that goes to cosine.
No, that was just another example.
Oh, sorry.
You were on page 2 and I had just jumped to page 5.
Why do they want to and pick out that's the true mystery.
And if you take the square root of what's in that red circle and erase it, then you get that black cell.
I nearly fell asleep. No, but I haven't figured it out.
You know.
All right, 7.5 applications. So that I don't get any interruptions, let's get all the groans out now. All right. So there's nothing new in this chapter, it's just applying the information that you've already got. So here we have a bucket. And the bucket weighs 20 newtons. If you're not a physics person, don't worry. It's 20 newtons. It's just an amount. And it's attached to a rope. And then there's a pulley up here. And the rope is 20 meters long.
Wait, yeah, Mr. Keeper, newtons are a measure of force, not of weight.
Well, okay. The
Force
force
the
that
natural force of the bucket.
the force that it would take to hold the bucket is 20 newtons,
Okay.
which means it weighs a force of 20 newtons. Okay. All right. It's filled with water. And there's 7.1 liters of water, which turns out to be 70 newtons of force, or the weight. And, we need some more physics people here. What is work? Force times distance. So, basically work is force times T. So the question is, how much work is done to lift the bucket of water?
So the bucket itself is 20 newtons? Or?
Yeah, the bucket weighs 20 newtons, the water inside weighs 70 newtons. So how much work is done to lift the bucket of water to the top? Oh, but I forgot to mention, the bucket is leaking. Oh, you got your groans out earlier. The bucket is leaking. And the total bucket will be empty at the top. So it's leaking constantly, and so by the time you reach the top, the bucket is empty. All right.
So it's
Now.
like the point that it reaches the top,
Yes.
What's that?
like the last drop.
Last drop, right as it reaches 20 meters. Okay? All right, what's the problem? Or what's the problem here in the problem? There's too many things happening, right? So, what we're going to do,
Evaporation.
Stop the evaporating. I mean, like, just figure out the rate at which it's
first, let's just figure out how much work it takes to lift the bucket. Oh, wait a minute, I forgot something else.
It's also
Wait. 0.4 newtons per meter. So every meter, it takes 4 newtons of force to lift it. So it's a heavy rope, and the bucket is leaking. All right, so what we're going to do is break the problem down. And that's the point of today's lecture, is to show you how to break things down. You can figure out how to figure how much work it takes just to lift the bucket. Then we'll figure out how much work does it take to just lift the leaking water. And then let's figure out how much work it's going to take to lift the rope, because the rope is getting shorter as you pull it up. All right, so let's start with the easy part. The work, lift the bucket. Does the bucket change in weight?
Yes.
The bucket. No, just the bucket.
No.
Yeah, the bucket doesn't change. It's lifted through a certain distance. Work is easy. Work is force times distance. The force of the bucket is 20 newtons. And we multiply it by 20 meters. I did something wrong here. I think the bucket was 22, so why don't we put it 22 as in my answers? We don't have to do all the work mathematically. Yeah, the bucket was 22 newtons. Sorry. It doesn't change any of the setup, but then at least we won't have to do all that math part. So we get, what's the work? 440 newton meters. Physics people, what's that? 440 joules. If you don't know what joules are, don't worry. It's 440 newton meters. All right. Now, the work to lift the water. What's happening here?
changing.
It's changing. So we're going to have to figure out how much work it takes to lift the water a tiny bit, and then the amount of water that's left another tiny bit, and the amount of water that's left a tiny bit until we've lifted it all the way. So we're going to have to do what? We're going to have to integrate. The integral is going to go from what? 0 to 20. And then force times distance, and the distance will be the dy that it goes up. So all we have to do is come up with the force that keeps changing because the water is leaking out. All right. What I do to make problems easy is I put in numbers and see what happens if I put in a number. So right now there's 70 tons. If I was to move up here, that's 70 newtons, 70 newtons. If I was to lift the water up 2 meters, if I was to lift the water up 2 meters, how much water is left in the bucket? Well, it's going out evenly.
Oh, we don't know how much.
What proportion is left?
7 comes out to 63 newtons.
1
9/10, 18/20, because you've gone up 2 meters of 20, so now there's 18/20ths left in the bucket, right? So at that point, the force needed would be 18/20ths of 70. When I go up to 5 meters, it's 15/20ths of the 70, and it would be all the way up to there. Where does this 15, 18 come from? What kind of formula? Instead of going 2 meters, I'm going to go x meters.
It was 63.
Was it?
Yeah, it was.
Okay. So if it's x meters, it's what? 20 minus x over 20. So the force needed is 20 minus x over 20, from 0 to 20, times 70. Because this is the ratio as it goes down. As the water goes up, or goes down, the ratio goes down also.
Don't want it to be wide.
Yes, this should be y. Or, what did I just say? I said x over there? Alright, let's just make it x then. That's fine. Okay. And so we integrate this. Well, that's easy. We'll just put what it is. Because if you divide 20 into 70, it is 3.5 times 20 times 3.5, 60, 70. So it's basically 70 minus 3.5x integrated from 0 to 20. And that turns out to be 700 joules or 700 newton meters. Okay? So we now have 440 joules lifting the bucket. We have 700 joules lifting the water. Now we have to lift the rope. Okay, so now what's happening when we lift the rope? The rope weighs 0.4 newtons per meter, so it's 0.4 times 20. But what's happening? Every time you lift it, there's less rope to lift. So you've got to lift so much of the rope this distance, but then it's a lighter portion, you lift this, and the lighter portion you lift all the way up. So we need to come up with a proportion for that. 20 minus x times 0.4. That would be the force needed, because it's 0.4 times the length of the rope, and whatever amount of rope we've lifted up, there's that much less force that we have to lift. So it's going to be 0 to 20. The force is 20 minus x times 0.4. Because when x is 0, the rope weighs the entire 20 times 0.4. And when x is close to 20, the weight of the rope is almost down to nothing. So you want this thing and that thing to make sense. Are you with me on that? Because that's going to play a big role in the next problem. You know, if you put a 0 in here, what that is saying is the rope is the entire 20 meters times 0.4, which makes sense. Then as you get closer and closer, you put in bigger and bigger numbers. Now the length is real small, times 0.4, the weight of the rope is going to be a lot smaller. Okay? You integrate that. Again, it's not too difficult. And it turns out to be 80 joules. So then, how much work is done to lift the bucket of water to the top when the bucket is leaking and the rope weighs that much? 440 plus 700 plus 80. Which is
1,240.
1190.
1100, 1220. Yeah.
Sorry,
Okay, any questions? And that's what you're going to have to do on some of the problems, is just break it down to simple things and then work with each one individually. Okay, here comes number 2.
We're ready for this.
Yes. None of these, I don't rank any of these really as hard like the chapter 4 ones.
You think they're easier than chapter 4?
I think so.
Do you think any of the next chapters will be as hard as chapter 4?
No, I think they all say about the
Shut up.
same. Okay.
What?
Okay, here is a bin.
Are we just doing 2 examples? Or
Yeah, just 2 examples.
Ice cream.
Here's a bin the size of the bin, it's a triangular shaped bin. It's
It's a cone.
it's a cone, a conical tank. All right, and it is filled to 8 feet. It's filled to 8 feet with olive oil.
I love olive oil.
And the density of olive oil is 57 pounds per cubic foot. Okay. And the tank is 10 feet tall. And the tank was designed by that formula. So it's a function, y equals 2x, and it was revolved around and it was created. Okay. How much work will it take to pump the oil out to the top surface? So you essentially, you're getting it to the very top and then it just leaks off. So all you have to do is lift it up to the top of the tank.
Mr.
Pounds, 57 pounds per cubic foot. So it's the olive oil is filled to 8 feet. It should be a little higher. It is not leaking. It is not leaking. Okay.
That's the density.
Area.
Yeah, you're in the right track. The problem is, how do you measure the weight of the oil as you're lifting it up? So what you do is change.
Yeah.
Change the oil to a bunch of discs. And then you take each disc, find out its weight, measure the distance that you have to lift it, and that's the work done. So you just simply take this liquid and slice it into a bunch of discs. And just figure out how much work it takes to lift this disc 10 feet, how much work it takes to lift this disc, and that disc, and so on. Okay? So, work is force times distance. The force is changing because each of these discs is a different weight. Distance is changing too. Each one goes a different distance. So there's a couple things to this problem. All right, first of all, let's figure out the force. What is the force? The force is the weight of each disc. The weight of each disc. So how do you find the weight of each disc? Force or weight is going to be the volume of the disc times its density. So what's the volume of a disc? Pi r squared times its thickness times density. That would give you the force of each disc. That make sense? All right. What's the thickness of each disc going to be? dy or dx? dy. So now we got the thickness as dy. So that means the radius has to be in terms of y. So what is this?
Y divided by 2.
What is this radius here? It's the x value. And so what's the x value? Y divided by 2. So that's the radius of each disc. So we take y divided by 2. The density is
57.
57. Okay, so that's how much force each disc is going to take. We okay? All right? So we got pi times y to the 4th over 4 times 57 times dy, where y represents the thickness of each disc. But now we have to lift each disc a different distance. the disc down here has to go a total of 10 feet. The disc here has to only go 2 feet. So we need to come up with something here, something there, and something there that will give us that combination.
Why is it wider before? Shouldn't it be wider second?
Thank you. Thank you. Sorry. Sorry. All right, so let's start out with this part here. What do you think we should go from?
0 to 10.
0 to 10? Probably 0 to 8, because this disc is at 0. This disc is at 8. Now, does that make sense for the radius? When we're at 0 here, does the radius have a 0 radius in our formula? Yeah. When we're right up here, does it have the appropriate radius? When we're at 8, the disc is supposed to have what radius? 8 divided by 2 should be 4. So that's good. So we're okay with that. All right, now, what do we want to do with this disc? We want it to go a total of 10 feet. So let's put 10. But we don't want this disc to go 10 feet. We want it to only go 2 feet. So when y is up here, we want that disc only going 2 feet. So what do we put here? 10 minus 1. Now let's see if it makes sense. When we're at the bottom, when y is 0, we want the disc to go the entire 10 feet. Is it going to go the entire 10 feet? Yes. When y is up here at 8 feet, we only want the disc to have to go 2 feet. And so if we plug an 8 in here, it's going to only go 2 feet. All right, so there's your formula, and then you just integrate it and come up with the value. And just working it out. Well, let's simplify it a little bit. So it'd be 0 to 8. This would be now that's just write it as 57 pi over 4. 10y squared minus y cubed. I guess that would be the easiest. I just multiplied y squared times this and grouped these numbers together. So now it gives you, and it turns out to be roughly 30,561 foot-pounds. Oh, does anyone know what that is? What's a foot-pound?
It's a hot mess.
I think it's called a slug.
Yes. Now we're just.
No one agrees with that? I think it is.
I
think a foot-pound is a slug.
Let's make it a foot.
I'll look it up.
Okay. Just leave it as foot-pounds. Okay. So, what did we do with this one? We sliced it into discs, so then we just measured how much weight or force it would take to lift each disc. And what did we have to account for? We had to account for the amount that they moved, and these two had to coordinate. We could have gone, no, I don't know if we could have.
Keeper, what's that number at the end supposed to be?
Which number?
3561, is that?
30,561 foot-pounds. That's what that integral roughly becomes.
Okay.
All right. Any questions? Any other questions you think of? All right. So that's what section 5, sum 5 is. It's just trying to put problems together, setting them up. I think this is the hardest part. Once you get it set up, you can use a calculator and just plug it in. So it's getting them set up. It's the hardest part. All right. I think I'm going to change the game. Well, no, I'll see.
I think you should change the game.
No, I don't know. I'll tell you on Monday what the game